Hello everyone, and welcome back to the Frontiers of Parameterized Complexity. We opened the year 2021, and our first guest is Magnus Wahlstrom from Royal Holloway, University of London, who will speak about compression and sparsification of multiway cut problem. Please, Magnus.
Thank you. So some of you may have seen a talk, quite similar talk with very similar title before. So this is based on an ICALP paper which says on quasipolynomial multicut and so on. For those who have seen it before, the difference here is that it's almost exactly the same result and proof, except this time it's constructive polynomial time result. But for those of you who only want the news, maybe come back in 20-30 minutes and we'll probably get into to the new stuff. So anyway, yeah. So the top and the result is I call it multicut-mimicking networks. You can also call it something like multicut sparsifiers, and we'll also talk about multiway cut kernelization. So the setup, the general setup, is that you have some very large graph with a small number of terminals. Your parameter k is the total number of edges incident with all terminals, just the sum of degrees of the terminals. And you're interested in all behaviors of the graph for any partition of the terminals. So, for example, the problem called the multiway cut is the problem where you have a bunch of terminals and you want to separate them into kind of separate connected components. So there is no path from one terminal to another terminal. So of course that corresponds to a partition of the terminals into 4 sets like this. So that's one partition we are interested in, but there could also be any number of other partitions. Like for example, maybe this partition is a little bit cheaper because you don't have to cut away quite as much, or an even cheaper partition is just to separate one terminal from all the others, and so on. So for all of these, we know that the cost of this partition, like the minimum number of edges to cut to separate them, is at most k, because if you just cut all edges instead of the terminals, you definitely partition the graph. And we want to preserve the actual minimum number for every partition. By the way, is my mouse pointer visible or not? Somebody want that?
It is visible.
It is visible. Okay, nice. Right. And what we're looking for is a smaller graph with the same set of terminals, such that for any partition, your big original graph and your small new graph have the same behavior. So for any request to partition these 4 vertices into 2 sets, if you can do it in this graph by cutting 3 edges, then you could do it in the previous graph by cutting 3 edges and so on. Slightly more carefully, if you have a set of terminals and a partition of the terminal set, a kind of partition cut, or how you want to pronounce it, is a set of edges such that in G minus X, every connected component of the graph contains terminals from at most one of these parts. So it's okay to separate more than you're asked, but you have to separate at least as much as this asks for. And a multicut-mimicking network, as we call it in the paper, is a graph where for every partition of T, the minimum size of a corresponding cut is the same in the input graph and the output graph. And the phrase multiway cut refers to a cut where every terminal has to be in its own partition. And finding the optimum value for any partition like this is NP hard as long as there are at least 2 parts. And if you ask to separate into 2 parts, then of course you can just do it via a graph min cut. So this is Edge Multiway Cut and all of its generalizations. And we will try to find, our goal is ideally speaking to find a replacement graph G prime, which has size polynomial in K. We will find one which is quasi-polynomial in K. And yeah, and I'll try to give some idea how. So the phrase, first of all, I only talked about partitions and multi-way cut and so on. The phrase we used is multicut sparsifier, and I'd like to argue that if you can mimic all partitions, they can also mimic all multicut instances in the following sense. Assume you have some, if you have a set of terminals T, you have some subset of some cut requests, like you're asked to separate 1 from 2 and 3 from 4, but you're not required to do any other specific separation. The argument is, as long as you have the same behavior for actual partitions, then you also have the same behavior for any multicut instance like this. Like original graph does, like maybe this represents the optimal solution for this multicut instance. And then this gives you a partition of terminals into connected components. And then your sparsifier or your mimicking network also contains a cut of the same cost for that same partition. So we can call them multicut sparsifiers while only thinking about partitions of the terminal set. Okay, I'll give a second if there's something unclear about the setup. As has been hinted, the reason we care about it is to kernelize multi-way cut, but it turns out the most efficient way to do that at the moment is to actually solve this much more ambitious question of all multicut specification.
But in the U graph, you don't allow weights, right? So all graphs are.
I don't allow weights, but since we have a parameter which is a cardinality of number of edges, you can just use parallel edges or something, and all these standard tricks if you want something to have weights. Okay, if you wanted weights which are different from cardinality, we're not dealing with those at all. Like if you try to solve a weighted problem parameterized by solution cardinality, I haven't thought about that question at all, and I think it might be quite different from the usual multi-way cut problem. So this is in this setting, right? So maybe that leads up to the next slide. The phrase for normal cuts, like just cut into 2 parts, is either called mimicking networks or cut sparsifiers. In the general literature, normally you allow arbitrary weights. So normally you parameterize by the number of terminals. So it's known upper and lower bounds for the size of a graph you need to have exactly the same behavior for all partitions of a terminal set into 2 components with weights and with unbounded terminal capacity. You can get it in double exponential in T, which when you think of it is not too impressive, given you could just write down the list of all min cuts in 2 to the T size. But at least some upper bound exists. There are lower bounds saying you need exponential in T. And for planar graph, there's some specific result that you need, that 2 to the order T is the correct behavior. So this is the sense, this is a term usually discussed in like the approximation literature and so on, sparsification. Because once you have the number of terminals as your main parameter, then you can allow weights on your edges as well. But if we parameterize by the total capacity, means sum of degrees, we know that for 2-way cuts, you don't need 2 to the T. You can get away with K cubed vertices for mimicking cuts into 2 partitions, and cuts into S parts is K. You need K to the S+1 vertices. So this is the, this is the 2012 paper with Stefan. And just two other notes about related results, again, from the approximation literature. If you're insisting that you only allow the vertex set to be exactly the terminal set, you get something like a log k-ish approximation with weights. And Julia Kirchhoff has some result with a constant factor approximation for a much harder question called like multi-commodity flow behavior being the same in the two graphs, which is smaller in size than ours, but not polynomial time, and some approximation. Okay. I think, okay, I'll go ahead. So what we are interested in is just the an exact sparsifier or a mimicking network whose size is determined by the total terminal capacity. So the result which we had last year already is that there exists a mimicking network with k to the order log k edges, but we don't know how to compute that one. And the second result, which we're able to get now, is that actually polynomial time, you can get something like k to the log cubed k. So the proof I'm presenting today is the general layout, the general strategy is the same as ICALP last year, but the actual machinery in the middle is replaced by a single observation, basically. So it's a slightly embarrassingly simple proof. The constructive result is new, and the gap between log k and log cubed k depends on approximation algorithms for some sparse graph separation question. So focus mostly on the existence, because as you might imagine, the constructive version is just a messier, more detailed version of the same arguments. So, right, yeah. Given the existence of a quasi-polynomial size mimicking network, there's a range of problems that get quasi-polynomial kernels, like, well, the problem Edge Multiway Cut, which is exactly the problem of separating a set of terminals into one specific partition, of course, as a quasi-polynomial kernel. Also, a few other problems on this list can also be reduced into a setting of, I have a bunch of terminals which I can detect in polynomial time, and there is some unknown separate partition of the terminals which corresponds to a solution. And if I have a mimicking network for the terminal set, I can kernelize these problems. Edge Multiway Cut, of course, is the major open question in among these. Edge Multiway Cut is the bigger question. The others are kind of harder problems, but they're maybe expected to follow if you get something real from Multiway Cut. So just brief history. So this is getting some time. This is getting some time ago. In 2008, we had the first tools for excluding existence of polynomial kernels, and quickly afterwards, there was a kind of flurry of research where we settled problems as polynomial or kernels or not polynomial kernels. I haven't mentioned what a polynomial kernel is, I realize. It's strictly speaking not necessary for the rest of the talk. If anyone incidentally needs a reminder, polynomial kernel is a routine. You have polynomial time to do simplifications until the size is polynomial in K in your parameter. So there were three questions among concrete problems which are kind of highlighted early on as being they look different than the others. We don't know what to do about them. Among these three, like odd cycle transversal was given a kernel within a few years using the tools tools which I'm also using in this paper. Multiway Cut is the one we're still bashing away at, and directed feedback vertex set has been completely resistant. I think we still have no idea about the directed feedback vertex set. There are some partial previous results, like Multiway Cut has a kernel if you're allowed to delete the terminals, or if the number of terminals is a constant. And also Multiway Cut has kernels on planar graphs and some stronger versions. But in the fully general version of Multiway Cut, we basically didn't have anything better than just run the FPT algorithm. Right. So the machinery in getting these kernels, I'll try. I will not attempt to give anything like a technical description of what's going on. Like behind the scenes, everything is advanced linear algebra and so on. But I'll try to just give what are the building blocks of the result and how can they be used. The general strategy in these kind of surprising graph separation kernels is representative families or representative sets. So you can think of it abstractly in the following sense, that assume that you're able to write some kind of a so offline. So before you get your problem, you're able to define a kind of query format Q, let's say, in the same sense that you might, that if you're solving a problem with, Korschell's theorem or advanced logic, you start by defining your problem by writing down a sentence in logic that exactly describes the solution set. So in the same sense, we are going to construct some form of a query object Q, which we can use to highlight solutions somehow. The reading of, it takes two parameters. Reading of Q x E is the edge E is not blocked by the query set X. So if you have your query Q and if you have the ground set, basically the set of edges of the graph, there's a polynomial time procedure which returns a subset of the edges in time, well, in time polynomial time, and size is a function of, well, function of Q and, actually a function of Q alone. So ideally we would like f of Q to be polynomial, but in this work we can't quite achieve that. And the guarantee you have on this much smaller output set is for every query X, either there exists an edge among the marked edges which is not blocked by X, or you have a promise that also all edges in your original graph were blocked by X. And what we're aiming for is that if there's an edge in the solution, an edge E, which is a part of the optimal partitions, for some partition of terminal sets, the edge E is required for an optimal solution. You want it to exist a query XE such that E is the only edge in the graph not blocked by X. So I realize again, this is a highly abstract description, but just in the abstract, if a set X sub E with this property exists, then the correctness of the representative set query computation here guarantees that E must be selected in the output. And the magical ingredient in this result is that you don't need to provide X in advance. You need an existence proof that says, I can show there exists a set X sub E such that the only edge in the instance not blocked by it is E. Then you have a guarantee that E is part of the output. So X sub E can be exponential time to compute. Like X sub E would usually depend on the actual solution. So with a little bit more detail what we're actually doing in constructing Q, as I said, there is some linear algebra in the background. You might think of it as having some kind of a very weird linear space with dimension e, so every edge in this index is one direction in the space. And you want a collection of spanning sets for some different subspaces, such that if you take the union of all spaces spanned by all of these individual layers, they cover exactly all edges in the graph except one edge E. So this will become much more concrete when we look at multi-way cut, but this is kind of the setting that we're working with. So your construction is the description of which layers you have. So in this picture, the construction Q has S layers. Each layer is of some specific type. And the size guarantee is the product of the ranks of these individual layers. So the individual layers are what we can use as building blocks. There are three types of layers which are important. One layer is, you might say, this is where the magic happens. There's a layer where kind of subspaces correspond to important separations in some graphs. A good sparse cuts in a graph, in some sense, correspond to low rank spaces, subspaces here. The only thing we need to use from this gamoid is to know that in any solution, one connected component of G minus X or G minus opt can always be covered by one layer of a gamoid. Second layer, there's some very technical name here. Technically, this is called a truncated graphic matroid. What we use it for in a construction is to have one layer where, with some rank parameter R, we can let the span cover all edges inside a and the rank you need to have is at least the number of vertices in these components in total. And the third one is called the uniform layer, where xi, the span of xi, only blocks itself, and you pay, well, basically the first and the third are going to have rank k, and the second one is going to be a much larger rank. You would like to use a combination of these different types of layers to say, by patching together different subspaces, one in each layer, I can describe a collection such that the union of the spans blocks all edges except exactly one edge from the solution. So there will be no more linear algebra in the rest of the talk. We just assume that these are the three different powers of the different layer types. The first one blocks one connected component. The second blocks a collection of connected component, but you have to pay more for the rank. And the third one just blocks the solution edges, basically. So an illustration of the 2012 result for multi-way cut. So assume that we're cutting that we have just 4 terminals. We want to compute a set like x sub e, such that for one edge in the solution to this separation, we want that all other edges are in the span. So we use a construction with 5 layers. The first layer, we use a gamoid. It's a gamoid layer. In this layer, we can use this layer to block out any edges inside component containing T1. In a second layer, so complete a separate construction, we can define a set of edges which blocks out all edges inside the vertex set of the second component. We repeat this in 4 different layers. You need a correctness proof, of course, to say that one gamoid can block out exactly all edges inside one component and no other edges. But this we have to take as a given because it becomes too much of a distraction to try to prove this. You might just, as a general idea, have the idea that the separation around one of these components is supposed to be a sparse cut in the graph. You're not supposed to be able to find an even better cut somewhere further off, because then you would be able to find a better solution. And now the only edges that we haven't blocked out are edges of the solution. So to complete the isolation, we add in the fifth layer where all the red edges, like all except one edge of the solution, are put in the fifth layer. And now you ask which edges are still not blocked out by this set X sub E. Well, any edge within a connected component is blocked by gamoid. Any edge between connected components, except the one we want, is blocked in the uniform layer. But the black edge between T2 and T3 will still be able to extend. It has not been blocked by any of these 5 layers. So therefore, we have a guarantee that this black edge must be discovered by the representative set computation. So since you have 5 layers and each layer costs k, the cost of this construction is k to the 5. So this is what works when you have a constant number of layers. And now we'll start thinking about what do we do if we want an unbounded number of layers, or up to k layers, not layers, but up to k components, sorry. And we want to use the same general tools. You can't afford to write down k different layers, because then your representative set collection would mark k to the k edges, and that's far too much. So you have to be a little bit more clever about it. And probably the idea that you should keep in mind for how this works is, let's say that you have, in this picture, you have a separation into 10 parts. And 10 is not a constant, like 10 is, I don't know, call it square root k if you want to call it k over 3 or something. Where you have 3 large components you can block by gamoids. So now we're writing a construction with like 5 layers of undefined cost so far. Where as before, we use 3 separate gamoids to block out the large components. And then we have the general promise is that after a couple of initial components, all remaining components are individually small. And in fact, the total number of vertices in the purple part is going to be, well, let's say k to the log k. So we get the quasi-polynomial number of vertices in the tail. And then just one more uniform layer to isolate like this one black edge here, which is being the one edge we want to discover. So if we have a structural guarantee that after some cutoff point, like the total number of vertices in layers in components 4 up to infinity is in total much smaller than the number of vertices in the rest of the graph, then we could use a construction exactly like this, and the cost for this one is the cost of this one is k to the 4 times our vertex bound on the purple part. And the proof will now be about how do we guarantee that you don't have an unbounded number of layers or components where each component is enormous. And this is the first new result or the first new ingredient. If you have seen this paper before, a very simple lemma. I'm claiming that if you sort the connected components of G minus X according to the number of edges around them, like a cut size, then component VI has at the most 2k divided by I edges incident with it. The reason is very simple, but also very specific to edge cuts. The sum of the number of endpoints of the solution in all components is exactly 2 times the number of edges in the cut, right? Every edge connects exactly 2 connected components. So the sum of the degree, so to speak, of the component is going to be 2k or less. And subject to this guarantee, the total number of endpoints in the first I components is at most 2k, of course, but also at least I times the number of endpoints in component VI, because V1 through Vi minus 1 are at least as big as Vi. So if you just say this, you say delta Vi is at most 2k over I. And we will need still some more machinery to really make use of this. But the idea is that given a guarantee that like component number 4 has some k over 2 or whatever edges around it, you can enforce a kind of sparseness in the graph that says that also means the vertex set Vi should be much smaller than the number of vertices in the whole graph. So okay, so the idea what we have available here. So we are thinking, or we keep illustrating it as a multi-way cut instance. What we actually have is some arbitrary partition of a terminal set, and we have a set of at most k edges, which separates this the terminals where every component contains terminals from at most 1 capital Ti. And we'll let V1 through Vs be the vertex sets of these connected components. So we are building a representative set query to block out all edges inside all components. We have 2 options. Intuitively, we have 2 options for how to deal with one component. The first option is if Vi has a large number of edges around it, we can afford to add one more gamoid layer to deal with that component, because there aren't too many components Vi with close to k edges around them. And if Vi is very small, like k to the c over k or something, then we can just place them in the graphic matrix layer and say that all of these together, all the small layers in total, a few vertices, and we can still pay for that. And in the middle range, we would have a component whose vertex set is large and whose edge cut is small. And then the idea is, if there exists such a Vi, like if T4, let's say, had only a very small number of edges around it, but still an enormous number of vertices, then it's very natural to say that the entire set of V4 along with these 3 edges could be replaced by a mimicking network for multicuts, treating these 3 edges as the new terminals, right? So you have, well, these 3 edges become new terminals, and you also have one old terminal inside the set. And any behavior that you want in the whole graph, not just for this partition, but for any other partition of the terminals, would be implemented by some partition of these 3 edges inside V4. So if we can somehow detect vertex sets Vi corresponding to very sparse cuts, we can shrink Vi itself and start over. And once we don't have such vertex sets, we also don't have the 3rd case in this case list. And at that point, we will be able to handle every component in the graph by either saying that it's one of the few large components, or it's a part of a relatively small tail. So now the interesting part of the rest of the argument is just assume that item 3 has been dealt with. Assume that there don't exist any cuts which are so sparse that we could shrink VI recursively, and then say, why is there a marking process that should work? So we're going to show so we have an algorithm. This is a non-constructive algorithm with something like k to the log k edges. So in phase 1, we look for any vertex set which has no terminals in it and whose number of vertices is bigger than number of edges around it to the power of c. Then recursively, we just create a new instance on GS. We sparsify or create a mimicking network for this recursive instance. And then we replace GS by the replacement in our graph and start over. Eventually, there are no sparse cuts in the graph anymore. So now the graph is quote unquote dense. So then we have a marking procedure, which is a representative set construction, which marks exactly k to the c edges and catches every edge which is required for some solution. If the graph has more than k to the c edges in total, we just take one edge which was not marked, contract it, and start over from step 1. Eventually, the graph contains k to the c edges in total, and that's the mimicking network. So we need an algorithm for detecting sparse cuts in step 1. And we need a recursive call to the same procedure. The algorithm is sweeping under the carpet. So let's just focus on the marking procedure for assuming that the graph is relatively dense. What does the marking step look like? So if you imagine, as I said, so every component has gradually fewer and fewer edges around it in some sense. Like V4 has at most 3k over 4 edges around it or something. So we're going to have a construction which looks exactly as the picture with the purple vertices. We have some G layers of gamoids for which you pay a factor of k in each layer in the representative construction, set construction. We have one final layer, which is the uniform layer of rank k. So the first G layers and the last layer in total, you have to pay k to the g plus 1 for these. Then you settle on some target rank, k to the d log k for the whole thing. And this gives you a limit of k to the d log k minus g minus 1 vertices, which could fit in the graphic matroid. So the idea is that you have G large layers, and you need a guarantee that the number of vertices in the tail is at most k to the d log k minus g minus 1. And that gives you k to the d log k edges in total, and then you can run the whole scheme again. And with the recursive density guarantee, this is actually quite easy. If you think about it, let's consider some solution where you sort the vertex set, let's say, in decreasing size. The gamoid layers will mark components V1 through VG, and the uniform layer marks X minus E. So the only thing we have to worry about is how many vertices are in the tail, like how many vertices are in VG plus 1 up to VS. By our observation, all non-gamoid components, like all components not handled by gamoid, have individually 2k over g or fewer edges around them. By the recursive density guarantee, a vertex set which has at most 2k over g edges around it, at most 2k over g to the power of c vertices inside it. And if you break this out, this is k to the d log k, so this is our total target size times 2 over g to the d log k. And now you just set, let's say, g equals 4, select 4 gamoid layers. I'm lying about the constants, but the principle is the same. So as long as this parenthesis 2 over g is some constant factor smaller than 1, it breaks down into k to the minus d, right? So 2 over 4 is a half, 1/2 to the d log k is, move the log factor down. This is k to the minus d. And d in this was just an arbitrary constant factor, which we defined in the construction of the query, of the setup. So if you let, according to this incorrect but principally correct picture, let d be large enough that this factor defeats k to the g plus 1. Well, k to the g plus 1 is just k to the 5. So set d equals 5 in this picture, and the total size of all smaller components is smaller, but smaller than k to the c by a factor of k to the 5. I think I'll pause here again and ask for a kind of clarification or audience questions, because I don't want this to look like an incomprehensible mess of machinery. This is really a simple argument, and this slide and this kind of one formula on the middle of it is exactly the place where everything happens. So if there's anything I can say to clarify the picture and remove some technicality, please ask. All right, so once again, the general picture was we can afford a constant number of layers with gamoids, which will handle the very large components. We have an analytical result that all components which are not among the G first must be much smaller than the head components. And there's also at most K such components in total, because they're just K terminals or fewer. And then the recursive, if component VG plus 1 had been too large, there would have been a sparse cut in the graph that we could have recursed on and recursively replaced. If the graph is sufficiently dense, like dense up to this guarantee in the middle of the slide, then this simple market scheme works. So this is actually more or less the complete proof up to filling out the coloring between the lines for getting the recursion to work right and working out the actual behavior with actually correct constants. But this is the whole idea. And the part which is not constructive is the density guarantee, meaning in the algorithm, the part which is not constructive is finding sparse cuts. Because perfectly finding a sparse cut in the graph is, well, you can do, I guess you might be able to do it in FPT time, but it's definitely not polynomial time. So we want to say if you only have approximately the ability to find a sparse cut in step 1, you need to tweak the constants in the scheme such that the marking procedure still works up to this approximate density guarantee. So for this part of the result, we'll need to look at approximation algorithms for finding sparse cuts in a graph. And our question for some exponent at least log k or worse, is there a set of vertices in the graph where, let's say, containing at most half the vertices, such that the number of edges around the set is smaller than the size of the set to the 1 over c, or equivalently, the set is larger than the cut size to the power of c. So you can also phrase it in another direction: is there a cut of some at most k edges such that both sides have size at least k to the c? Or alternatively, if that's not true, this is the approximation guarantee. Otherwise, you promise me that the number of edges around any set is at least cardinality to the power 1 over c divided by alpha. So alpha is approximation. So this exact question for this very high exponent hasn't been considered at all, obviously. There's a lot of research on finding sparse cuts in a much stronger sense, weaker sense of sparse, like stronger sense of density, where basically instead of constant c we just have 1. So we just want to optimize the ratio between the cut and this vertex set. So the technical question which fits closest is called small set expansion. The edge expansion of a set is the number of edges around it divided by cardinality. The problem small set expansion finds a vertex set of size at most some rho times n to minimize the edge expansion value. This problem has seen a lot of interest in approximation. It's connected to this question called the unique games conjecture. Like it's known that there's a conjecture, hypothesis, or what if, a hypothesis saying that small set expansion might be hard to approximate to constant factors. And that would imply the unique games conjecture. And we want some approximation algorithm factor with anything better than log n. And if you look at what's available, if you want to optimize the expansion without worrying about the set sizes, you get the square root log n approximation. This is not applicable to our kernel at all because we really need to be able to focus on just subject to the cut containing at most I for I less than k edges, what's the worst case. So cuts through half the graph are not useful to us. And the kind of unconditional approximation without footnotes and without any footnotes and asterisk attached is an approximation factor of log n. And log n is exactly the approximation algorithm factor that we can't use in the scheme because you end up with a factor of log n in the exponent of a kernel size. You have a kernel guarantee k to the log n. And there's a more advanced version which says if you take into account both the size of the whole graph and the size of the set we're looking for, there is a problem, a result of Bansal et al. From, more recent than the others at least, which tells us that's an approximation factor of log n divided by square root of log of the set you're looking for. The extra guarantee is square root log n times log 1 over rho. If you look at our application situation and shuffle the constants around, you say that the ability of the Bansal et al. Algorithm to find a sparse cut is an approximation factor of log n divided by square root of log vi. The only lower bound is the lower bound against the constant factor approximation. And they're under our hypothesis. So it's not so much a lower bound as it is somebody's hypothesis that this problem doesn't have a constant factor approximation. And for completeness, I will show two slides of basically formulas here, but I'm really just taking this approximation guarantee of this slide, plugging it into exactly the same setup as last time around, and showing it's possible to find values of number of gamma layers G and kernel size C to get the scheme to work. So we have a polynomial time randomized guarantee that says for any set of at most n half vertices, after all recursive sparsification calls are done, the number of edges around S is at least cardinality to the 1 over C divided by alpha, which if you plug in the formula for alpha is S to the 1 over C times square root log S divided by log n. C is going to be log cubed K in this picture. We have two parameters we want to set. The first parameter C is our target kernel size. So we're gonna cheat on this one. We're gonna say, so C, so when I say we have to set the value C, I mean our marking scheme will mark exactly k to the C edges. We have to make sure it doesn't mark the whole graph. So I'm gonna set C equal to log n divided by log k minus 1 round down. The only guarantee for this is k to the power of C is less than the whole graph. And we assume that this is at least log cubed. So k to the C, the number of marked edges, is just slightly smaller than the whole graph. Then we set the number of gamma layers to something square root of C log k. The failure scenario for the marking scheme is you have some solution where the tail components contain too many vertices in total. So if we assume that there is one component vi whose size is at least k to the C minus g minus 1 or C minus g minus 2 or something like this, like too large for the scheme to work, and we plug into the density guarantee, we know vi is at most, we reshuffle this, we say we know that vi is at most approximation factor times number of edges around vi to the power of C. If you just plug in delta vi is order k over I, or k over g rather. And also we kind of plug in n, we compare that log n is essentially log C, log n is essentially C times log k. Then all the factors I just introduced cancel each other out. The reason behind this is not very interesting. This just tells you this is the threshold that you should aim for. And after all these factors cancel each other out, then the upper bound on any component after the g first ones is some constant less than 1, like you can make this be 1/2 if you want, to the power of log cubed k. So before we had g equals 4 and the parenthesis just 2 over g. Now it's some bigger, more complicated formula, but the principle is the same. You can make the second part just be essentially 2 to the minus c. So if we just plug the same things again, every component after the first g components contains at most this number of vertices, which you rewrite as k to the c times 2 to the minus order c. We want the guarantee that this bound should be smaller than k to the c minus g minus 1. So k to the c times this thing is at most k to the this thing, if and only if c is at least g log k. Like if I collect everything to the exponent, on the left side you have 2 to the c, on the right side you have 2 to the squared c squared log k times another log k factor. Reshuffle, square both sides. You can verify setting c equals log cubed k or larger guarantees that this inequality will hold, and that means up to some. So you run the scheme up to some cutoff point at k to the log cubed k edges. At that point you stop trying, but up until that point you will always manage to mark all vertices in the tail components, because you can't have too many vertices in that part of the graph. And this is all randomized polynomial time. So we show there exists a mimicking network for multicuts of k to the log k edges. You can build one of k to the log cubed k edges. Edge Multiway Cut, Edge Multicut under some different parameter, and so on, have quasipolynomial kernels. Immediate questions: vertex deletion version. But you can't at the moment, you cannot possibly hope for a constructive version for vertex deletion, but even an existence question for vertex deletion looks harder than this. Second question, there was an incorrect claim in my ICALP paper. I claimed something I called a metric sparsifier. The proof fell apart. I also don't know if it's false. So I will be curious about whether this is true or false. There's a stronger notion of sparsifier investigated by Chushoy, where current bound is an approximate result of k to the log k. You might want to investigate the behavior for that. And you might want to prove that the Edge Multiway Cut has a polynomial kernel. Thank you.
Thank you very much, Magnus. So, time for questions, if there are any. Well, one of two, right? Either the talk was very clear. Yes. Anyhow, thank you once again, then Magnus. Yes, thanks a lot, and see you the next week, right? Okay. Bye.